Good morning, dear students. Welcome back to Target JEE Class 12 Physics. We are in first lesson Electric Charges and Fields. Today, our concept for discussion is Coulomb's law and its limitations. If two charges plus Q1 and plus Q2 are there and they are at distance r. Here, in between charge Q1 and Q2, vacuum is there or air. So that is the medium between two charges. These are the conditions for Coulomb's law. These two charges are point charges and they are not moving. In that case, according to Coulomb's law, the force of repulsion or attraction, if like charges are there, repel each other. If unlike charges are there, they will attract each other. That repulsive or attracting electrostatic force we used to call F proportional to Q1, Q2, and the force between the charges is inversely proportional to square of the distance between them. This very relation is called inverse square law. From this, we can also get the formula F1 by F2 is equal to R2 by R1 whole square. So this relation also important for problems. If we merge these two statements, then the force is equal to, see this proportionality symbol we have to replace with is equal to, we have to multiply with some constant into q1 q2 by r square. This is the formula. When do this formula is applicable? If two charges are point charges and they are not moving and vacuum or air is present. Particularly this term epsilon naught, this is called permittivity of free space. Free space means vacuum or air. Permittivity of free space epsilon naught value is 8.85 into 10 to the power of minus 12 Coulomb square per Newton meter square. This whole term 1 by 4 pi epsilon naught, this value is 9 into 10 to the power of 9 Newton meter square per Coulomb square. This we can also give a symbol small k. Then the formula becomes F is equal to k q1 q2 by r square. Like this, in a short form, we can remember. This q1 charge will be repelled in this direction. This is the force on first charge because of second charge. And the q2 also repelled by this positive charge in this direction. So this is the force on second charge because of first charge. These two forces are equal and opposite. So F1, F21 bar is equal to minus F12 bar. This force is in positive direction, this force is in opposite direction. So magnitudes are same, but these forces are equal in magnitude, opposite in direction. One force is acts on one body, another force acts on one body. So these forces we can say, these forces are action, reaction, pair. So in Newton's third law, for every action there is an equal and opposite reaction, the action-reaction pair. See, these forces are acting along the line joining, this is the line joining these two charges. So whether it is F21 or F12, they are acting only along the line joining the charges. They are centers of the charges. They are not moving, they are not acting in any other direction. So we can write these forces are central forces. So central forces are those forces which acts along the line joining the centers of a body. Here centers of a charge. Vector form let us write. So vector form F21 bar is equal to K Q1 Q2 by R 21 square into R cap. Like that we can write. This 1221 is not necessary. You can remember like this for examination point of view. You can write like this. F is equal to K Q1 Q2 by R square into R cap. This is one form of vector form of force. If you want to write R bar here, see, this force is along the line joining the two charges. That is the meaning of this R cap. This is along the R bar direction. So R, we can also as well write F is equal to K Q1 Q2 by R cube R bar. So be careful. If you write R cap, this is R square. If you write R bar, it is R cube. Why? Since R cap is equal to R bar by R. This relation we know. So in the place of R cap, if we write R bar by R, so one extra R will come in the denominator. If this is the origin, this is x-axis, this is y-axis, this is O origin. Suppose the charges are in the space. If the charges are in the space, this is Q1 charge and this is plus Q2 charge, and this is R1 bar. This is a position vector. The position vector of Q2 charge is R2 bar. Then the distance between Q1 and Q2, this R is equal to R2 bar minus R1 bar. Right? So if that is the case, this is the direction of force on second charge because of first one. This is the direction of force on first charge due to second one. So in this case, the vector form we can write F is equal to K Q1 Q2 by, in the place of R square we will get R2 bar minus R1 bar whole square into R cap. R cap we can write R2 bar minus R1 bar cap. So we can also write this K Q1 Q2 by this R place, you have to remember this formula, into R cap. So R is equal to, see, this is a triangle of vectors. This is the direction of this one. For Q1 to Q2, this is the direction. So if two forces are taken in represented by the sides of a triangle taken in order in reverse direction, this is the resultant. So by triangle law of vectors, what we can write, R1 bar plus R bar is equal to, this is R bar is equal to R2 bar. So R bar is equal to R2 bar minus R1 bar. This is the vector form of Coulomb's law. If two charges are there, this is plus Q1 This is plus Q2. Then the between them vacuum is there or air. This is the direction of force on second one because of one. This is direction of force on two, one because of two. If they are like charges. If they are unlike charges, plus Q1 minus Q2 and distance between them is R. As usual, vacuum and air is there. This is the direction of force on first charge because of second one, and this will attract like this is the force on second one because of first one. The force formula F is equal to 1 by 4 pi epsilon naught into q1 q2 by r square. This epsilon is a property of a medium. Property of a medium is there. This force whatever we have defined, Coulombian force, Coulombian electrostatic force, depends on the medium between the charges. So if only vacuum and air is there, this formula we can use. If there is a medium between them, then what happens? This is the charge plus Q1 and this is the charge plus Q2. R is the distance, but here vacuum and air is not there, some medium is there. Some medium is there. Then what happens? The forces, the direction of forces are same. The direction of forces will be same. This is the force on first chapter, first one because of second, but here vacuum is there, here medium is there. Then this force formula becomes like this. F is equal to 1 by 4 pi. Here epsilon of the medium we have to take. If free space we have taken, why? Because here vacuum and air. Whenever vacuum and air is present, we say permittivity of free space. Here when medium is there, we have to take the permittivity of the medium. Q1 Q2 by R square. To distinguish, I will write this is F naught. Epsilon m medium permittivity formula is epsilon naught and epsilon r. This is permittivity of a medium This is permittivity of free space. This is called relative permittivity. This relative permittivity also called as dielectric constant, and the symbol we use is K. From this formula we can also write relative permittivity is equal to permittivity of the medium by permittivity of free space. So this formula we can also write as this formula. We can write like this. F is equal to 1 by 4 pi epsilon naught epsilon r q1 q2 by r square. This epsilon r can also be written as K. So F, this is medium force. The force when medium is present. So 1 by epsilon r is called as K, dielectric constant. So I can write like this. 1 by K into 1 by 4 pi epsilon naught q1 q2 by r square. So this is F naught. So I can also write Fm is equal to F naught by K. From this discussion, what we came to know is the force of repulsive force or attractive force, Coulombian electrostatic force in a medium depends on dielectric constant. We came to know that the Coulombian force, the electrostatic force in a medium, depends on the dielectric constant of a medium present between the charges. How it takes place, let us see. If between two charges, this is plus 1 charge and plus 2 charge, the distance between them is k. So if I place a vacuum or air, if I place two charges q1 and q2 in vacuum and air, the force between them, if the vacuum or air is present between the point charges, for air and vacuum, k value is 1. For air and value, k value is 1. Then that in that case, f value is maximum. So when do the electrostatic force between two charges will be maximum? If and only if a vacuum or air is there between the charges. If the charges are, if the metal sheet or metal is present between the point charges, if metal is present between point charges, between vacuum and air is not there, now point charges, what is there? This is q1 and this is point charge q2, and in between this distance is r. So sorry, this distance is r, and here metal is there. So if metal is there, for metals, k is equal to infinity. If k is equal to infinity, in this formula, if you put k infinity, 1 by infinity is equal to 0. So F in metal is equal to 0. That means minimum. In third case, if non-metals or alloys, whatever they, non-metals present between the point charges, so between q1 and q2 some glass is there, some mica is there, like that insulators, non-metals are there between two charges. The k value lies between 1 is less than k less than infinity. K value is between 1 and infinity. So in this formula, Fm is equal to k naught by, f naught by k. If k value, increases, then F value, electrostatic force, I write a symbol Fe, electrostatic force value decreases. So here F value will be in between the maximum and the minimum. So these points you have to remember. So we came to know that if two charges are there, how to calculate the Coulombian force or electrostatic force. If three charges are there, how to solve, how to calculate the force. Let us see. Let us take an example of three charges. I may take this is x-axis and this is y axis. So at the origin, we have placed a minus q charge, and here at some distance a, I have placed another charge plus q. Here at some distance here, another minus q at b distance I have placed. So I have to find the net force on minus q. We will give some names. The q which is at origin, I'll give this q at q1. I will give the name q1. This is q2. This is q3, like that. So find the net force on q1 along x-axis. So if this is the question, let us solve this. See, this minus q, this is the x-axis. So net force along x-axis acting on q1 we have to calculate. So this minus q1 is attracted by this plus q1 in this direction. This is the force on charge q1 due to q2. That is the force. And this minus q will repel this minus q1 in this direction. This is the force on first charge due to third charge. And these two angles are equal. So F13, if we take the components of, if we take the components of F13, this is F13 cos theta. Why? Because it is adjacent. And this is F13 sin theta. So net force acting on Q1, therefore net force acting on Q1 is equal to force on first charge because of second one and force on first charge because of third charge and sin theta. So now let us solve this one. So net force is equal to force on first one because of 2 is K, Q. These charges are, let us take the charges are equal. Q1 is equal to Q2 is equal to Q3 is equal to, let us take this is Q. Then what happens? This is Q square by the distance is A square plus this this repulsive force 113 F13 KQ square by B square into sin theta. So if I take a common KQ square, then 1 by A square plus 1 by B square sin theta. This is the net force acting on minus q1 along x-axis. Like that, we can calculate the net force using electrostatic force formula, Coulombian force formula among the charges. Let us consider another example involving 4 charges. So let us consider a square of side A and at A corner minus capital Q is there. At B corner another minus q. At C corner, another minus q. At D corner, another minus q is there. So three charges, four charges. At the midpoint means wherever the diagonals of this square intersect each other, this is the midpoint. At midpoint, one charge q is there. So we have to calculate if the system is in equilibrium, find q. That is the question. If the system is in equilibrium, find this q value. Let us see what are the forces acting on minus q1. So minus q1 here will repel this q1 in this direction. This is the force due to the charges at CD on C because of D. This is another force. These two, this is the force on D because of A. Here I did mistake. Force on the charge D because of C. These two forces are equal. Why? Because this formula is K q square by A square. This value also K q square by A square. So these two forces are equal. So let me name it as F. So if two forces are at 90 degrees, if two forces are acting at 90 degrees, this is force F, this is force F, this is the origin. The net force is root 2 F. This we know in vectors lesson. So this value is here root 2 F. F value is this one. And now this charge Q also present here. This charge minus Q also present here. This minus Q will repel this minus Q in this direction. So this formula is K Q square by the distance. This is A, this is A. See like this. This is A, this is A. Then this is root 2 A. So this is root 2A whole square. So the net force on minus Q is equal to net force on minus Q is equal to root 2F plus KQ square by this is 2A square. Now system must be in equilibrium. That means what? This small q must attract this minus q towards it. Then all forces get nullified and equilibrium point we can reach. So here the force, this I'll give some name O. Force on D because of the charge at O. That must be in opposite direction. So this charge must be a positive charge. Then only positive charge will attract this negative charge. So here this net force must equal to the force on D due to O. That is equal to root 2 F value. What is the F value? KQ square by A square plus KQ square by 2A square. So force on D due to charge at O, this value I will calculate. See, OD distance is, this OD distance is, total distance is root 2a. So this distance is a by root 2. So this value I'll write FDO K capital Q small q by a by root 2 whole square is equal to, here, root 2 kq square by a square plus kq square by 2a square. So further I simplify it like this, k capital Q small q by, this is a square by 2 is equal to root 2 k square kq square by a square plus kq square by 2a square. Now the common things on both sides, let us cancel. kqa square, kqa square, kqa square. Then what remains here? 2 small q is equal to root 2q plus q by 2. Then 2q is equal to, I will take the LCM, 2 root 2q plus 1 by 2. Here q will be there. Then q is equal to, I will take this 2 common and q common. So q by 4. So what comes here? The remaining root 2, 2 root 2 plus 1. So this is the value of charge Q at O. That charge must be positive so that it can attract the minus Q there and nullify the forces in opposite direction. Like this, we can calculate the forces in various cases. If several charges are there in a place, so let us take this Q1 charge as reference charge. One more charge is there here plus Q2, and here one more charge is there plus Q3. Here one more charge is there plus Q4. So here four charges are there. This charge, this positive charge Q2 will repel this Q1 in this direction. This is the force on first charge due to second charge. This Q3 charge also repel this Q1 charge in this direction. This is the force on Q1 due to third charge. This charge Q4, which is there here, so this force, it will repel this in this direction. This is the force on first charge because of fourth one, right? You can also imagine here one more charge plus Q5. So this Q5 will repel this Q1 in this direction. This is the force on first charge because of 5 charge. Like this, several forces are acting on Q1 charge. But one thing, the net force, if you want to write, this Fn net force is equal to force on first charge due to second one, force on first charge because of third charge, force on first charge because of fourth charge. Like this, force on first charge because of 5 charge. So the sum of algebraic sum of all forces is equal to net force. So this is called superposition principle. The superposition principle says that the force between any two charges is not being affected by the presence of other charges around the charge. See, The force between 1 and 2 is F12. This magnitude or direction of this force is not affected by the presence of Q3, Q4, Q5 other charges around this Q1 charge. This is called principle of superposition. According to the principle of superposition, the net force is the algebraic sum of all forces acting on the charge. But here it is algebraic sum is suppose for example only two forces are there, 1 2 and 1 3. Two forces are there. Angle between these two, the angle between F12 and F13 is equal to theta. Then the resultant force, net resultant force, magnitude is equal to, we know it, this is 1 2 square plus 2 F12 F13 cos theta plus F13 square. Using this formula, we can calculate the resultant magnitude of resultant force. The direction of this resultant force also we can calculate by using the formula F13 sin theta by F12 plus F13 cos theta. By using this formula, we can also calculate the direction of resultant force. This is the principle of superposition. The Coulomb's law is having some limitations. Let us see what are the limitations. First one, in the statement itself, we have taken point charge applicable for point charges only. Second one, the charges should not move. Applicable for static charges, not moving charges. If we want to apply the Coulomb's law, in the case of big bodies, let us take a sphere, conducting sphere. Two conducting spheres I have taken and I have charged them. So the sphere is A is having charge and B is also having some charge on them. Always when we are calculating the distance between them, center to center distance we have to take. This is the distance between these conducting spheres. See, if we want to apply Coulomb's law Q1, Q2, so this charge is Q1, this charge is Q2. If I want to apply KQ1, Q2 by R square formula, I cannot calculate the correct force. Why? Because here positive charge come closer than the positive charges on the other side of the sphere. When the charges, positive charges, like charges come closer, they repel each other. Because of repulsion, what happened? All the forces, they will be repelled and move back from its position. So charges will be going back, going behind this one. So charges are actually here, but we are taking the distance this one. But this distance also, the quantity of charge here and here also we cannot calculate perfectly. So as distance changes, the Coulombian force magnitude also changes. That's why we cannot apply the Coulomb's law for the bigger bodies, big sized charged bodies. How? Let us consider two conducting spheres now. This conducting sphere radius is r and this conducting sphere Also, this conducting sphere radius is also r. The distance between them, center to center distance we have to take, is small r, and they carry charges on them, q charge. This is also carrying same charge. When can we apply the Coulomb's law for this case? If and only if the radius of the sphere is much lesser than the distance between the spheres, then we can apply Coulomb's law. If the size of the charged object is less than the distance between the charged bodies, we can apply Coulomb's law. Here the concept of Coulomb's law ends. You can watch the video having some problems on this concept and get a thorough knowledge about application of this law in problems. Thank you.